Welcome to Ask and Learn.
So for this problem, we have the charge of a deuteron, which is just the charge of a proton. We have the voltage, the current, and then the mass of a deuteron, which is the mass of a proton plus the mass of a neutron. So the first thing you want to do is find the velocity of these deuterons. And to do that, we're going to use the energy. So the energy is equal to VQ, and then we can set that equal to the kinetic energy, 1/2 mv squared. If we solve for v, we find that v is equal to square root 2 times the charge times the voltage over the mass, and that's equal to about 1.38 times 10 to the 7 meters per second. So that's the velocity of the deuterons. Next, we want to find the time between each deuteron. And so we know that the current is delta Q over delta T. So we can solve delta T is equal to delta Q over the current. Delta Q is just going to be the charge of one deuteron, and we already have the current. So delta T is equal to about 1.6 times 10 to the negative 14 seconds. That's how long it takes for one deuteron to pass through. And then, using those, we can solve for the separation using the equation V is equal to the separation over the time it takes one deuteron to pass through. So we can solve that for R. R is equal to V delta T, and that's equal to about 2.2 times 10 to the negative 7 meters. So that's our answer for part A. Then for part B, we want to know if the electric force of repulsion affects the beam stability. And so to do that, we're going to solve for the acceleration of one of the deuterons due to the electric force from another. So we know F equals ma, and so acceleration is equal to force over mass. And we're looking for the electrical force here, and so that's K times Q squared over R squared m, and that's equal to about 1.4 times 10 to the 12 meters per second squared. So that is a significant acceleration, so the beam stability is affected by the separation between the deuterons.